Now let's go through some magnetism problems. Remember, there are only two formulas we're using. The force on a current carrying wire is ILB, where I is the current, L is the length of the wire, and B is the magnetic field strength. Or F is QVB, where you have a charge moving in a magnetic field, and Q is the charge, V is the speed of that charge, and B is the magnetic field. You're going to have to be able to find the direction. Now remember, use your thumb as the direction of the current or the direction of the velocity. L is the length of the wire. Now this is not really a direction. You're kind of combining I and L together here. And B is the magnetic field strength. Now put your fingers in the direction of the magnetic field strength, and the force will be in the direction of your palm. If you have a negative charge, then just figure it out, and your answer is going to be the opposite of whatever you found to start with. Let's try one. A proton, okay, protons are positive, of charge 1.6 times 10 to the negative 13 coulombs, 19 coulombs. This is our charge Q. Is moving east. Okay, so I'm going to start here with the velocity is going east. Experiences a force, F, of 8.8 times 10 to the negative 19 newtons upward. Okay, so upward means it's coming up like this. Due to the Earth's magnetic field. At this location, the magnetic field is B, 5.5 times 10 to the negative 5 Teslas to the north. Now we're going to assume this is north, okay, and this is B. This is our diagram. Let's see, find the speed of the particle. All right, let's see, Q is 1.6 times 10 to the negative 19 coulombs. F is 8.8 times 10 to the negative 19 newtons. And B is 5.5 times 10 to the negative 5th Tesla. And we're looking for V. Now I know F is QVB, so the velocity is the force divided by the charge divided by the magnetic field. So the force is 8.8 times 10 to the negative 19 newtons. The charge is 1.6 times 10 to the negative 19 coulombs. And the magnetic field is 5.5 times 10 to the negative 5th Teslas. And you get 1.0 times 10 to the 5th meters per second. Now, let's see if I did this diagram. Let's see if we gave you the problem correctly. B is your fingers, so point your fingers north to the top of the page. V is the direction of the particle, so that goes to the right. Now, if you hold your hand like this, where the top of your page is north, the bottom of your page, ooh, sorry about this, is south, east, west, all right, is the force up? And it turns out, yes, it is. So we did give this to you correctly. Now, if an electron, now electron means whatever we get, we're going to flip our answer for direction with charge of 1.6 times 10 to the negative 19 coulombs. Experiences a downward force, F, of 2.0 times 10 to the negative 14 newtons, while traveling in a magnetic field, B, is 8.3 times 10 to the negative 2 Teslas west. What direction was the direction and magnitude of the velocity? All right, let's go on and figure out the direction. An electron experiences a downward force. So F is downward. So this is F. All right, while traveling in a magnetic field, that is to the west. So B is to the west. Because remember, north, south, east, west. Put this on your paper. Okay, this will help you orient yourself. And then it's up and down out of the paper. All right, so let's see. B is to the west. What is the direction of the velocity? Put your fingers to the west. Now the force is down. All right, If you do that, you should see that your thumb, I'm going to do this in dotted lines, your thumb is pointed downward towards south, but it's an electron. Because it's an electron, you know the velocity has to be to the north. All right, so the direction is north. Had it been a proton, the direction would have been south. All right, so now that's kind of the challenging part of these. Now let's find V. F is QVB. So the velocity is the force divided by the charge times the magnetic field. So this is 2 times 10 to the negative 14 newtons divided by the charge, which is 1.6 times 10 to the negative 19. You see how I'm not putting the sign in? Because we're finding out the direction with our thumb, with our hands. 8.3 times 10 to the negative 2 Teslas. And we get 1.51 times 10 to the 6 meters per second. And then we know our direction is north. Now, what if we have a wire? A magnetic force acting on a wire that is perpendicular to a 1.5 Tesla, so that's B. Whenever you see Teslas, you know it's magnetic field, is 4.4 newtons. That's my force. If the current in the wire is 5 amps, so I is 5.0 amps, what's the length of the wire? Now, we're not given directions, so we're not going to mess with them. All right, I know the force is ILB. We're looking for L. L is force divided by IB. The force is 4.4 newtons. The current is 5 amps. And the magnetic field is 1.5 Teslas. And we get 0.59 meters. Now, an electron moving north encounters a uniform magnetic field. If the magnetic field points east, what's the direction of the magnetic force on the electron? All right, let's see. Electron. So I know whatever I get, I'm going to flip. Is traveling north. So the velocity is to the north. If the magnetic field points east, so B is east. All right, because remember there's north, south, east, west. All right. Find the direction of the force. Put your thumb, and I have to do this every time, folks. Put your thumb to the north and the magnetic field to the east, and you see your palm is pointing down. All right? Your palm is pointing down, but it's an electron. So you know the force has to be up.